All right, it's week 2 of Lab 7, the spectrum of iodine and its analysis. As I said last time, and we'll go through again this time, what we're after is to use the spectrum of iodine, here it is down here again, all with all the peaks assigned, in order to get 6 different numbers. So the depth of the well in the excited state, the spacing between the vibrational levels in the excited state, the sharpness of the well in the excited state, the spacing between the levels in the ground state, the spring constant in the ground state, and then finally the gap between the bottom of the well in the ground state and the bottom of the well in the excited state. And we're going to get all those values basically to be able to reconstruct the energy spectrum and energy structure of the iodine molecule from this spectrum and all these little sharp peaks. And we talked last time about the fact that there's sort of 3 different groups or manifolds or bunches of peaks, one corresponding to each vibrational quantum value for the ground state, so the origin of the transitions. So the V equals 0, ground state V equals 1, V equals 2. What we have, our primary way of analyzing things, are energy eigenvalue expressions for the Morse potential, or for the simple harmonic potential for that matter, and which we'll use for the ground state. And here it is. We didn't talk too much about it last time. We won't talk about it even as much this time. But it gives all these little level values in the excited state and likewise also in the ground state. It's the differences between any one level in the ground state and any one level in the excited state that gives us a peak in the spectrum. So each peak in the spectrum, each of these little mini peaks, that one for example, corresponds to a different ground state level going up to a different excited state level. And so what we want to do in order to compare to experiment is take differences between these two expressions. And that's what I've done here. And we'll actually use this expression later, but the first part of the analysis, I mean, these are still quite complicated expressions and hard to extract data from in their current form. To make that simpler, we take differences between adjacent peaks. So that means taking differences between neighboring peaks. So for example, between 30 and 31 here, those two or any other pair that are neighbors to each other. And that expression, when you take those differences, basically the difference between this guy for V equals some value, and the other one for the value incremented by 1, then you get a delta V value, and that is something that's pretty simple. It doesn't even depend on the ground state value of V. It doesn't depend on V double prime. It only depends on V prime. It's linearly related to V prime, and it leads to the Birch-Sponer plot that we talked about last time. If you plot this delta V value, the difference as you move along the spectrum, the difference between adjacent peaks as you move along the spectrum, within one manifold or within one bunch that corresponds, so within all the red guys or within all the blue guys or within all the green guys, but only within one at a time, and plot those differences versus the value of V prime, then you get this straight line. You should get a straight line. You do get a straight line, in fact. And the slope of the straight line gives us some of the values that we need, these correction terms that account for the fact that it's not a pure harmonic oscillator. Gives you the spacing between levels in the excited state, and it gives you this third quantity Vc prime, which is the value of V when you're right at the dissociation point for the excited state. All these are excited state properties, quantities. And then the spacing is one of the quantities we want directly. The quantity that's related to the slope gives us the narrowness or the sharpness of the curve in the excited state. And a little bit of monkeying around shows us that the depth of the well in the excited state is YAC. We can also get from the values that we got from the Birch-Sponer plot. So using the Birch-Sponer plot and these relationships, we get 3 of the values that we want. We have 2 left to get. One is the spacing between levels, vibrational levels in the ground state. Another is the spring constant or force constant for the ground state potential. And we can get both of these by looking not at adjacent values between the V prime levels within one group here, but by looking at values, peak differences between peaks that have the same V prime value, the same value on the upper states, so as shown here in the upper state, but are different by 1 in the ground state, as you can see here down here. Every one of those differences should be equal to, so in the ground state we're going to ignore all of these terms, all the terms that account for the fact that it's not a perfectly harmonic well, and that's because in the ground state it is much closer to a perfectly harmonic well, and we're only looking at the first 3 levels anyway, so the corrections aren't needed. We can get this WE value no matter where I put these guys, right? If I take all these guys and start shifting them to different possible pairs, I can get, where was that now? There, yeah, there. I can get an estimate or a value for WE for each pair. So I'm going to get a lot of different values. I average them all, however many pairs I need. And that's my official value for WE double prime, the spacing between levels in the ground state. So now I have, and then from that, and using this relationship, I can get the force constant in the ground state. And so now I have 2 more of the values that we want, and the only value that remains is this energy gap between the 2 electronic manifolds. And we can get that now because we have this expression. This expression gives the wave number for every peak in the spectrum, every single one. So all these peaks should be given by this expression. Again, assuming this stuff is 0. And we now have all the parameters that we need in order to actually plot out that spectrum, except for this offset value, which is exactly the value we want. It's proportional, well, omega EL is this divided by HC. So giving omega EL gives us this EEL as we want. So all we have to do is plot the actual data, so plot the peak positions versus the V prime number for a fixed value of V double prime. That should have a V double prime there. And then plot the same thing but using this expression as a function of V prime. and then adjust this offset between the two until they overlap. Down here shows how that works. It really works well. The theory behind this is really accurate, and that means that our fits should be really good like this. I mean, you can see, I'm not even sure which of these is experimental and which of these is the theoretical fit. I think the orange guys are the theoretical fit and the blue guys underneath are the experimental, but it hardly matters. There's almost no difference between them all. And of course, you just adjust, I mean, these two sets originally started offset from each other, and you just adjust the offset, and that offset is the number we want. And you can do that both starting from V double prime equals 0, from the ground state 0, the ground state of the vibrational level and the ground electronic state, or for V double prime equals 1, or for V double prime equals 2. So there's 3 possible fits you can get, and you can verify that all of them work well. This is for the V double prime equals 0 case, which gives us the longest and best progression, and therefore probably gives the best value of the offset. But these others should work and give values that are pretty close as well. All right, I don't know if that's clear. I hope that's clear. We'll talk tomorrow again about this stuff, and you can ask questions at that point. The analysis is more complicated in this case than for earlier labs. Next week's lab 8 on the spectrum for HCl, is just as complicated. So if you're a little bit confused about how to do this, do lots of work to get unconfused this time, because we're going to do something similar next time. All right, that's it.